Hello everyone. So the topic for today is we are going to solve an example for optics. We have an object that is placed behind the converging lens. Then after the converging lens, there's another material that has a different refraction index, and we would like to see where exactly the image is going to be constructed, like after the lens itself or in this system. So let's do it. Basically, we will have the center line here, and we have an object. Let's say this is the object itself, and the object has height of 20 millimeter. Then we have after 80 millimeters, we are having a lens. This is going to be a converging lens. So the distance here between the object and the lens itself, distance of the object is equal to 80 millimeter. Then we have also, after this, another material after 80 millimeters. This is another material, and this material has an N of 0.342, and the N here is basically error, so its N is equal to 1. The focal length of this converging lens, it is 45, so it's approximately here. Okay, so it's here, F, and this is 45 millimeter, a distance of focal length. So we would like to see where exactly the image is going to be constructed. So to do this, basically we have to start by getting from the tip of this object a ray that is going horizontal, the central line. Then basically from here it's going to go through the focal point to hit the new material. Okay, so after hitting the new material, basically this is a different material. This is n equal to 1, this is n equal to 0.342. That means there's some refraction or total reflection. We don't know actually whether this light ray is going to bend inside this new material, so it's going to go somewhere like this, or it's actually going to reflect back here. And to know this, basically we need to measure or to calculate the angle here, the angle of this ray with the surface itself, with the vertical surface or the new material. So this incident ray angle. Okay, so to get the incident angle itself, we know that this angle is equal to this angle. Okay, so we have here, this is 45 millimeters and this is 20 millimeters from the height of the object. So that means tan theta incident is equal to the height, which is 20 millimeter, over this part, which is 45 millimeter. And this basically gives us that theta incident is equal to 24.2, so it's 24.2 degrees. So theta incident is equal to 24.2 degrees. Then from here, to know whether it's doing total reflection or total internal reflection or refraction, we have to measure the theta critical. And theta critical itself is basically equal to sine minus 1 of N2, which is N2 over N1, which this is going to be sine minus 1 of 0.342. So from this, we will know that theta critical is equal to 20 degrees. 20 degrees. Okay? So that means that the theta incident is bigger than theta critical, and that means we have a total internal reflection. So the ray here is going to go like this, and the theta incident is going to equal to theta reflected. So theta incident here is equal to theta reflected. Okay, and all of this is equal to basically 24.2 degrees. Okay, so let's write here that theta incident is equal to 24.2 degrees, and let's continue our analysis. So we are going to remove this part, sorry. So after having this ray horizontal, we need to have another ray that goes through the center point of the lens from the tip of the object. So it's going like this. Okay. So basically it's going this way. Okay. Passing through the center point. So from here, we need to know exactly how much the theta incident in this case. So let's say this is theta incident 1. Okay. So we need to see how much this theta with this like new material. So let's say this one is going to be, the angle here is going to be theta incident 2. Theta incident 2. Okay. So to get theta incident 2, basically this theta, it's equal to this theta. Okay. Incident 2 is 1. So theta incident 2 is equal to basically tan minus 1, the height, which is 20, over the full length here, which is 80. And this means basically the theta incident 2, it's equal to 14 degrees. So that means that theta incident 2 is less than theta critical, and that means we have a refracted signal. So this ray is going to be refracted inside the new material here. Okay, it's here. So we can see that these two rays are going to intersect where? It's basically intersecting here. You can see this one is reflected back and this one is incident, so they are actually get connected here. So the image is going to be created at this location. Okay, this is our image. So basically what we need to compute right now is the distance of the image and the height of the image itself. Okay, this is what we need to find. But how to find this? Okay, this is the critical question now. So if we would like, let's remove this part so that we can show this. So let's maximize, or let's draw this portion bigger. Okay, so basically we have this portion, this part, so we have this like this. Okay, then we have this line and it's reflected, and we have that this angle is theta incident 1, which is equal to this one, theta incident 1 as well. Then we have another ray here, which basically it says that this ray is going like this. Okay, and it's going to reflect back inside, but we don't care about this. And basically the angle here is going to be theta incident 2. Let's say here theta, this angle is theta incident 2. So we have this angle and we have this angle. So what we need is basically to find how much is this, basically from here to the top. So we can say that the height of the image is going to equal to, from this ray, let's say this one is going to be D1, okay, the center line to the first ray that hit this new material, so it's D1. Then basically let's say that this additional height, this small one, is equal to h. Okay, so we can say that this is equal to this one is equal to D1, and this one is equal to h. So the height of the image is going to be equal to D1 plus h. So this is what we need to compute right now, D1 and h. Okay, to get D1, this is D1, so we will use this triangle basically. So this theta incident 1, which is equal to 24.2 degrees, and this distance basically is 80 minus 45, which is 35. Okay, and from this one we can say that the tan theta incident 1 is equal to D1 over 35, and from here we get D1 is equal to 15.6 millimeter. Okay, so let's write at the top D1 is equal to 15.6 millimeter, and also theta incident 2 is equal to 14 degrees. Okay, so we have D1 from here. Okay, so we'd like to find the h itself. So let's see how are we going to find the h. So from here, if we were to basically divide this triangle into two halves, basically drawing a horizontal line here. Okay, so let's say we need to have this like value of this line, which is equal to d, for example, and we can see that d itself, okay, it's going to equal to, let's say, from this graph, when you have the second line that going through the central point, it went to this point here, hit the new material in this point, so we see this is d2. So we can see that d here is equal to d2 minus d1. Okay, and to find d2, basically we can say that from this triangle here that we have on this one, we have here this theta, okay, and this theta we computed it was 14 degrees, okay, and we have that this distance is equal to 80, that d2, so we can see from here that tan 14 is equal to d2 over 80, and that means d2 itself, which is equal to 20 millimeter. Okay, so from here we can say that d itself is equal to, d is equal to 20 minus 15.6, which this is equal to 4.4 millimeters. Okay, so this d is equal to 4.4 millimeter. So let's remove all of this, then continue our analysis. Okay, I know it's a bit hard, but you can do it. Okay, so from here we have the d. We need to find the h, which is this part, h. Okay, so we can say that this part, the rest of the part, is equal to d minus h. Okay, let's call this distance, the horizontal distance here is equal to L. Okay, and from geometry we know that theta incident here, these are two parallel lines, and this is the same angle. So this is theta incident as well. This is theta incident 1, and this angle is equal to this angle here. It's equal to this angle. So this is theta incident 2. So from here we can say that tan theta incident 1 is equal to H over L. H over L. And tan theta 2 incident 2 is equal to, from here, D minus H over this line, which is L. Okay, so from here we have the angle. Okay, we don't have the L or the H here, so let's basically equal in these two formulas. So from here, this means that L is equal to H over tan theta 1, and from this one it says that L is equal to D minus H over tan theta 2. So if these are equal, we equal these two together. So basically L is equal to this one, equal to D minus H over tan theta 2. So we have theta 1, we have theta 2, we have D. That means we can get H, and H in this case is going to be equal to, H is equal to 2.82 millimeter. So from this H that we got, we can find the height of the object, which is equal to D1. D1 was equal to 15.6, as we know, 15.6 plus 2.82, which means the height of the object, it's equal to, by the end, 18.42 millimeter. Okay, so from this we can get also the L here, the L value. We have the H right now, so we can get the L. So the L is 6.35 millimeter. So this is the L basically. This is small portion, which is this side. Okay, let's just make this one here. On H. So we can know from here, we can know that the distance of the image is equal to total distance between these two, which is 80 millimeter, and minus the L. This is the L. Okay, this is the L, which is basically equal to 6.35 millimeter, which means that the distance of the image is equal to 73.65. So we got the distance of the image, we got the height of the image itself, and by now we have solved the problem. I hope you enjoyed the video, and if you like it, please like and subscribe, and wait for me for another example on this topic. See you and have a good day.